Hello, everybody. Hello. Hello. Hello, my name is Troy Livingston, and I am the Director of Development and Strategic Partnerships at the Museum of Life and Science in Durham. I want to welcome you all to our first Science Cafe. We're putting on, the Science Cafe is a collaboration between the Museum of Life and Science, Sigma Xi, the Scientific Research Society, and Nova scienceNOW. We have a producer here from WGBH with us. You'll notice that we're lit and mic'd and cameras here, and I hope that the cameras don't make anybody nervous. They shouldn't. The whole point of tonight is to have some fun, listen to some folks talk about some interesting science topics, and unlike the Titanic, we're not going to predict unsinkability. And so we hope that you all will work with us to create a fun environment. We're hoping that you all are willing to ask questions. There are no stupid questions here tonight. The whole point is that we're doing this for a public audience. Hopefully we have some scientists in the room, and a lot of us are lay people like me who are just interested in the topic and enjoy thinking about and talking about science with friends. And obviously we've decided to hold it in an environment where adult beverages are okay. And you might think of this as kind of the anti-lecture hall, where kind of anything goes. The room is somewhat smallish. That's by design. If you need to get up and take care of anything like a beverage refill or restrooms, for example, which are located to the far end of the bar and make a right-hand turn in the event that you need those during the course of the evening, please feel free to do that at your convenience. A couple of things, and I want to get you all participating a little bit before we go right into our speakers here. Just a little quiz here, and put your hand in the air if you know the answer. The rise in temperature that the Earth experiences because of certain gases in the atmosphere, like water vapor, carbon dioxide, nitrous oxide, methane, the methane trap energy for the sun. What is this called? Somebody? Anybody back there? The greenhouse effect. Yay, all right. Is the greenhouse effect a good thing or a bad thing? Anybody? Somebody new? Right? It's a good and bad thing. Very good, yeah. This is an interesting explanation. So without these gases, right, heat would escape back into space, and Earth's average temperature would be about 60 degrees colder. Okay, so keep that in mind, because I'm going to give you another fact in a minute that's pretty interesting. So in the last 100 years, the Earth's temperature has warmed by about how many degrees? Anybody with a guess? 2 degrees. I have 1 degree. 2 degrees. I have 1 degree, but I'll give you credit for 2. Although that would be a huge order of magnitude difference. Maybe Rob can talk about that. Okay, the 4 warmest years of the 20th century all happened in which decade? Back there. The 1990s, right. Very good. Now, here's where we come back around. At the peak of the last ice age, when glaciers covered much of North America, which was about 18,000 years ago, the average temperature was how much colder than today? Somebody with a guess? 3 degrees. Good guess. Anybody else? 5 degrees. We're getting closer. You guys are very cautious. It was 7 degrees. 7 degrees. So imagine if those greenhouse gases weren't there, right? And it was 60 degrees colder, we'd be a big block of ice floating through the... 2 degrees. Yes. Very good question. No, it was Fahrenheit. It was Fahrenheit. So, true or false? Is the global climate becoming more variable or extreme? True or false? Is the global climate becoming more variable or extreme according to NOAA's National Climatic Data Center? It is. It isn't. It is. According to them, it's false. On a global scale, now this is important, on a global scale, I'm setting up Rob here for his talk. On a global scale, there's little evidence of sustained trends in climate variability or extremes. But this perhaps reflects inadequate data and a dearth of analysis. However, on a regional scale, there's very clear evidence of changes in variability or extremes. So answering it true and false is really not possible. But anyway, I'm hoping that's a good setup for our first speaker, Rob Jackson. He's the director of the Center on Global Change at Duke University. Dr. Jackson is a professor in Duke's Department of Biology and the Nicholas School of the Environment and Earth Sciences. He heads up an interdisciplinary institute studying the problems presented by climate change. In a 2004 paper published in the Proceedings of the National Academy of Sciences, Dr. Jackson analyzed existing research data to figure out the quickest route to cutting U.S. emissions of carbon dioxide by 10%. And I'll let him tell you more about what they decided. So, Rob? Thanks.
Thank you. Well, thanks, everyone, for being here. Can you hear me in the back? I'm sorry?
Just keep the volume up.
Keep the volume up. If I start to drift off, please let me know. So what was the first thing I learned in college? Well, the most important thing I learned in college was you can have beer or you can hear, but you cannot do both. And as Troy mentioned, I direct the Global Change Center at Duke. I'm in the Nicholas School of the Environment and also in the Biology Department. And I'm here to tell you a little bit about climate change, fuels, why we need a transformation in energy, and then what some of the impediments to that transformation are. So that's where we're heading tonight. So I guess I start my own PowerPoint presentation, if you would. Now, they told us there would be a screen here tonight, which literally is true, but it's a small screen. So we will we'll minimize the data and talk about the concepts. So why do we need hydrogen fuel cells, right? That's the first question. We're here to talk about hydrogen and transforming the energy use and technology for the U.S. The reason we need to do that is because if we continue to burn fossil fuels to the extent that we possess coal and oil and other fossil fuels, then we have a problem. And that problem is climate change. So these two bookends from the last decade sort of set the two edges of the debate. On the left, we have the Atlantic Monthly drifting towards disaster. This was an article about U.S. energy policy or the lack of a U.S. energy policy, the recent energy bill notwithstanding. On the right, you have the economist view, staying cool about climate change. So somewhere in between is where we reside. If I could have the next one, Martin. So let's dispense some things about climate change first. The reason we're talking about climate change at an energy forum is because climate change is the reason that we need to transform our energy. Now, Troy already talked about some of the issues, what we know, what is less certain about climate change. Let's talk about a few things that we know. He talked about how extreme events and such, it's not clear yet whether we are seeing more of those. There's been recent evidence that not so much the number of hurricanes has increased, but the energy in those hurricanes, the intensity of those hurricanes has increased for simple physics. The ocean is a little bit warmer. When that ocean is warmer, there's more energy generated in those storms, and the winds are greater. So hurricanes are something. Let's talk about temperature. A red dot here means warmer. And for those of you in the back, this is a map of how temperature has changed from 1976 to 2000. A red is warming, blue is cooling. A big dot is warming or cooling a lot, and a small dot is warming or cooling a little bit. So what do you see, first of all, in the graph? Yeah, I'm seeing red, right? There's an awful lot of red. If you ask me, is the warm snap we're experiencing tonight due to global warming? I can't answer that question. Nobody else can. But scientifically, what we can do is look at what's happening across broad areas of the Earth and asking, how is that changing?
First 25 years of the 20th century, how would that warming compare?
So there have actually been two. So the question was, if I put up a map of the first 25 years of the century, how would that compare? It's interesting because warming in the 20th century occurred in two phases. It occurred in the first 30 years or so that was due in part to changes in the sun's intensity. Then there was a gap of about 30 or 40 years where it didn't change all that much. And then about 1970, it started going through the roof. So this would be a little bit faster, but not completely out of line with what we saw in the first couple decades, about twice as fast or so. Does that answer your question? Well, I'm referring to the IPCC data set that shows that I'm talking about global temperature trends over the 20th century that shows a rise up until about 1930, a relative stabilization, and another rise beginning about 1975.
No, I was taking exception to the characterization that this latest rise is twice as fast as the initial rise.
It's faster. It's not literally twice as fast. I don't know exactly what percentage it is, somewhere between 1 and 2 times faster.
There's less data in the southern hemisphere. Is that changed?
No. So where there is no dot, that's a good question. Where there is no dot means we have no data. So down here, you have a few stations in Antarctica, here in the southern hemisphere, large areas of the southern oceans that we have no data whatsoever. But the question is right. I mean, through the tropics, for example, you see relatively small dots. Where do you see the biggest dots? Up north, that's right. I mean, so what are we talking about over this 25-year period? Where you see a large red dot, that is 4 degrees Fahrenheit from 1975 to 2000. That is a huge amount of warming. And what we're seeing in northern latitudes is sea ice melting up in the Arctic. People are talking about, models are suggesting that the Arctic will be ice-free possibly by the year 2100 or 2150. With some benefits, if you can sail a boat across North America, with some costs to the things that live on that ice, polar bears, seals, seabirds, the Inuits who use that ice to hunt, things like that. This is going to take longer than we thought.
So why the big temperature change down in Antarctica below South America, right there? Is it too large?
Here. So what's happening around Antarctica, there's a lot of controversy about whether Antarctica is warming or cooling. What Antarctica appears to be doing is warming around the edge and being relatively stable in the center. You have to remember the Antarctic continent, the average temperature is about minus 20 degrees. Right, so we are in no way close to melting Antarctica's ice completely, despite what you might hear in some articles or on television. Right, it's a long way. But around the edge of Antarctica, you're seeing the fastest warming on Earth right now. And the second fastest is at polar latitudes in the north, the boreal forest and the tundra.
Getting back to the pros and cons of warming, what about the rise in sea level as I've heard associated with the...
Okay, good segue to the second question. The question was, what about rising sea level? So this is a global picture. What I hope to show you, to convince you in this picture, is why 99.9% of scientists aren't talking about whether global warming is occurring anymore. All right, you look at that map, there's a lot of red on that map. Let me go to the next slide. So there's not much debate in the scientific community about whether warming is occurring. The question was about sea level rise. Let's bring this home. Let's not talk about global pictures now. Let's talk about North Carolina. What you see here is in the inset, so eastern North Carolina. The light blue is ocean currently. The intermediate blue is what is underwater with a sea level rise of about 1 foot. What is dark blue is what is underwater with a sea level rise of about 3 feet, 1 meter. All right, so somewhere, the projections for this century, the 21st century, are that will be somewhere between that, probably closer to 1.5 feet, perhaps 2 feet. Not entirely clear. So what do you notice about that figure? Now, I don't know about you, but that's a scary figure to me. Look at the Outer Banks. We're talking about a lot more ferry rides to visit what's left of the Outer Banks. All right, this is data. These are data of Ben Poulters, who's a grad student at Duke. I'd like to credit him for this. That's a big change. That's not, even the dark blue, that's not out of the question that we could experience this century. That's probably a little high for what we'll experience this century. But we're talking about huge changes along coastal North Carolina. Is there a question? A question in the back.
This is based on a static analysis. This is looking at current contours and saying that if the sea level rises 1 foot, land that's now at a certain elevation is inundated. But the processes that build beaches and barrier islands are dynamic. And there's no reason to be certain that those islands would necessarily be totally obliterated.
Well, the other issue, of course, is that are factors that contribute to subsidence as well. So I don't I can't answer your question completely, to be honest. Does anyone from the audience have a comment on that?
As you say, another factor in Barrier Island mechanics is that you would expect an inward migration of that Barrier Island with sea level rise.
Perhaps, that's correct.
To what extent our efforts to try to harden them would prevent that from occurring, or try to raise the level of those islands. But
so the comment was about the migration of that Barrier Island. True, great idea. What's the problem with the migration of the Barrier Island? What is it? We got houses on the Barrier Island. It's no consolation to a house owner to say, well, that's okay. The Barrier Island is going to be half a mile or 100 feet or 100 yards over here. Their house is over here, right? So we're fixed into keeping that Barrier Island where it is, or we have to transform the places that we build or don't build, or we're going to lose those houses. So this is for the children in our room, it's possible we'll be at this light blue area in your lifetime. Let's keep going, because we're going to have to play with the time a little bit here, and I think in the presentation we'll have to both combine some of the question and answer that we had allocated to that before. All right, now let's talk about energy. What I tried to do, I just wanted to take a few slides to convince you, one, that global warming and climate change is real, and two, that it's not some abstract phenomenon. This is something that affects us in every way of our lives, and will in this century in North Carolina. So now let's talk about energy. That's the subject for tonight. And I think some of you in the back, or most of you in the back, can still see this. What we have here is a pie graph of the United States' carbon dioxide emissions. It says 2002. Those numbers still hold for the recent 2004 emissions. So we have about 1/3 of our carbon emissions coming from transportation, cars and trucks, planes. We have about 30% coming from industry, and about 38% coming from residential and commercial real estate. Which one's growing the fastest? Okay, try again. Residential. If you want to look at the sector of the economy where energy use and carbon dioxide and fossil fuels are going up the fastest, it's us. It's residential use, in particular home use. All right, so that's lumped for residential and commercial. All right, transportation's a relatively close second, but it is second. So we are the source, the greatest source of increase, the heating and cooling of our homes. All right, but so as we talk about, and Tom will talk about transforming the energy of our nation, we have to think about this as our mosaic. It's every segment of our society that this includes. What I'll talk about tonight, obviously, we're honing in now on transportation and why transportation is a relatively easy plum to pick from the tree. One other number to keep in mind is this number of 1.6. Now that big P and that little G, that's a petagram. That's one of those jargon words that Troy was talking about. That means a 1.6 followed by 15 zeros. Right, so one of the things to think about is we're talking about big numbers here. Small effects are important, but if we're going to make a difference in this carbon budget, we're talking about large scales and lots of something, and we'll come back to that point later. All right, so 1.6 petagrams of carbon. Now the only data graph I have in here, and I'll try and walk you through this as quickly as I can. This is from a paper that Bill and I did and that Troy referred to. Here's that same petagram number up here, but now instead of 1.6, which is off the top, we've got 0.5 up here, 0.3 here, and 0 here. So what are these numbers? Well, the most important number for us tonight is over here on the right. These are the emissions from our transportation, just the cars and light trucks and SUVs we're talking about. So light blue here is our car emissions from 1970 to 2000, so over 3 decades. The red is the SUV and light truck emissions from 1970 to 2000 in petagrams of carbon. So what do you notice about those bars? The SUVs and trucks where the growth has been. Okay? Now what's this number, about 0.3 petagrams? So approximately 20% of our fossil fuel emissions come from our cars and our light trucks. And the growth of that primarily in the last 30 years has been the increase in SUVs and trucks. So here's an interesting fact. You ask somebody, how has the mileage improved of cars and trucks and SUVs over the last 30 years? The mileage of cars has gone up. The mileage, the miles per gallon of trucks and SUVs has gone up. And what has our fleet mileage done? It's been stagnant. It's like 2 batting averages. It's like, comparing batting averages over the course of a baseball season. It's not the average that counts. It's the total amount. And what's happened is although both sectors have improved in their efficiency, you've had a shift towards this less efficient sector. So our fuel mileage is static now at 20 miles per gallon, and it has been for approximately a decade. The green is asked, all right, on this side, if we could cut emissions, which we're coming to from cars, we can cut back some of those fossil fuel emissions. The green is to take the opposite approach. That's to use trees to scrub out carbon from the atmosphere, to use the leaves that they talked about on the video. And what the purpose of this analysis was to ask, how could we reduce our fossil fuel emissions by 10%? What would it take? What it would take for plantations is 100 million acres of land. All right, so it's essentially taking 1/3 of our agricultural land and growing trees on them. So that's feasible, that's possible, but I just want you to think about the scale of that. That's an area the size of California with lots of other changes. So this is going to take a major transformation of our agriculture and other things if we want to go down this path. So we'll contrast that then to the sources of emissions from cars. All right, now why is this depressing? 1908, Henry Ford, the Model T, 20 miles to the gallon. Today, the U.S. fleet average, 20 miles to the gallon. Now that ought to make you angry. I mean, that is ridiculous. You know, granted, the cars are faster, they're safer, they're better, they're a lot more comfortable. That is a national tragedy right there. This is something that we could have done something about, and for all of Jimmy Carter's faults, this is something that Jimmy Carter got right. And if we had listened to Carter, we'd be in a lot better shape now, as we were in a war in Iraq and other places, than we are today, because we've had no effective policy, almost no increases in CAFE standards, and things like that. So that's the depressing comment. What's the optimistic comment? So we'll talk about several ways that tomorrow is here tonight. One of them is through hybrid technologies. The Prius, the Honda Insight, the Prius and the Honda Civic were the first ones to be mass marketed in this country, get between 40 and 50 miles a gallon. Okay, so that's an approximate doubling of the fleet mileage for the U.S. Where would that take us if we could implement that for the whole fleet? What it would do is it would cut our fossil fuel emissions by 10%. So we'll come to hydrogen here in a second. We produce in the U.S. 6 to 8 million gallons of oil a day, okay, depending on whether you include liquid natural gas and other things. We import about 11 million gallons a day. If we made that one change to double our fuel efficiency, utterly feasible with current technology, not 20 years from now, right now, we'd save about 3 million gallons a day. Now imagine you woke up in the morning and there was an article in the paper saying, discovered in the U.S., 3 million gallon a day oil field. That's almost a 50% increase in our oil output. That would be major news in this country. Okay, you talk about Anwar. Anwar is just a drop in that bucket. Okay, what I'm saying is that we can make that 50% increase. It would be the same as finding that $3 million a day oil field just by transforming our fuel efficiency. That's all it takes. We could effectively cut oil imports from the Middle Eastern countries. So now let's talk about hydrogen, which is where we're ending. And I promise I'll end here quickly, and we'll get to Tom's important points. Why hydrogen? Well, why hydrogen? Because, for several reasons, it's a terrific energy distribution system, or it could be. At the local source, there's no pollution. Right now, so in addition to the energy benefits, you get rid of a lot of the ozone problems, the ozone alert days, and many things. So there are all kinds of reasons to be in favor of transforming our economy with the use of hydrogen. And look at that car. Is that a sexy car or what? I mean, it just makes you want to get in there and drive with hydrogen. So then you got the details over there on the left, right? And the details they hinted at in the video. Where does the hydrogen come from? Okay, don't let anyone talk to you about hydrogen without telling you where that hydrogen will come from. Is it going to be a coal plant? If it's a coal plant, it might be good for air quality in the city, but it's a net loss in terms of energy efficiency. All right? Is it a nuclear plant? Okay, how's that trade-off sound? Take a nuclear plant, great source of energy, you use that to generate hydrogen, then we can run our vehicles on that. We don't emit fossil fuels for the most part. Or ideally, it would be renewables, right? Solar, windmills, and such. The problem with solar and windmills is that the sun doesn't shine all the time, the wind doesn't blow all the time, right? So you need a way to store that and to move that energy around. Hydrogen provides us with that mechanism, but we just have to make the hydrogen. And I think that's a subject that Tom will continue on. Two last points. One is about population. Okay, this is the projections for North Carolina by the year 2050. We have about 8 million people now, 10.5 million people by 2025, 12, 13 million people by 2050. All right, so all these things that we do, we're talking about a lot more people and a lot more people using energy. So it's going to take radical transformations in our energy source to cut fossil fuel emissions. And I hope genuinely that hydrogen can do it, but hydrogen won't be able to do it alone. It's going to take a lot more renewables or nuclear or coal or something else to make that hydrogen. And then finally, and I'm closing, this is a subject that I care a lot about. A couple of years ago, I wrote a book on this subject. And in a sense, that book contains my feelings about this, which are that we should spend a lot of money investing in hydrogen and a lot of money investing in some of these newer technologies, but that shouldn't be all that we do. That we should do the sure things now. This is like your home bank account. You know, you're hemorrhaging money for 1 year. What's the best thing that you can do for that? You can spend less. All right, and if you want, and the analogy to spending less here is to cutting our fuel emissions directly and not using trees to scrub it back out of the atmosphere, which will help and we should do, and not using many of these other approaches. But the first action should be to cut emissions, and that's my take-home message. So thank you for listening.
Quick check-in with you all. Do we need a quick break? How are we doing? We okay? With that said, I want to introduce our next speaker, Thomas J. Meyers. He is the Airy Distinguished Professor of Chemistry at UNC Chapel Hill. Dr. Meyers is a professor in UNC Chapel Hill's Department of Chemistry. He's a former Associate Director for Strategic Research at Los Alamos National Laboratory, where he worked on implementing a national research and development strategy geared toward providing the energy technologies of the future. So Dr. Meyers published nearly 500 papers and is one of the most highly cited chemists in the world. And so please welcome Dr. Meyers.
First of all, compliment you for coming out and also for the organizers for this spectacular venue. We have a noise problem, but I've always had this dream of giving freshman lectures in a bar, and at last I can do it. It's terrific. I think we've been off to a really good start. I want to come back to this issue of fuel cells, and I will, but I think I would like to start by first addressing some of the issues that Rob brought out and rising up to a relatively high level to look at where we are as a nation and world in these apparently difficult times, talking about, on one hand, the environment and global warming and shortages of fuels. I think I should first develop some perspective. And as we have done so far this evening, if I say something silly, ask me a question. If you've got something really good to say, break in, because I probably don't. Anyway, let me first do some advertising. I extracted what I'll say tonight from a talk I gave a couple of years ago. It was at a symposium in honor of Neil Lane, who was presidential science advisor under President Clinton. And I started out, and of course you can't see it from the back, but I simply want to point out in this slide there are a series of reports. One of them was mentioned in the introduction to fuel cells. We, in fact, have some scholarly background in individual areas, all of which have been covered tonight. I would make the point, if you look down at where we are in terms of public policy, our real problem is bringing all these together in a very coherent way, and you'll see this message unfold as I go on. Let me turn to the first slide. There are two issues that are driving changes in the world that will occur much more profoundly and rapidly than you think. I would argue in the next generation, in this generation and the next, the most pressing issue we will face is energy and the environment. And a first observation when you're in this business is you do not think of the two separately. It is not possible to think about energy and not at the same time ask the question, what are the environmental impacts? And I'll talk about energy first, and then I'll say something about environment, although that's been well covered by Rob. A first observation, if you look at where we are as a nation in terms of our energy supplies, as you can see from that first bullet, we import about 8 million barrels of oil a day. That grew 2% last year. Energy demand globally is predicted to increase by straight line projections by a factor of 3 by the year 2050. Notice also this is a global issue. That growth will not be in this country. It will not be in Western Europe. It will not be in Japan. It will be in India, in China, and East Asia, period. And that growth is out of our hands as a nation. First observation, global. What I say about things that we can do and think about mean we have to find ways to translate them into our political spectrum and then to those spectrum of other countries. This is going to be a shocker maybe. Oil production may well be much less than has been projected. There was a recent book, for example, that suggested that the highly vaunted reserves in Saudi Arabia may be clearly overstated, well overstated. If this is true, this need to find different sources of energies will, in fact, be upon us much sooner than anybody thinks. This particular observation will lead me to fuel cells because transportation is a real key here. Oil is a magical thing. It's a magical thing created over millions and millions of years because it's a liquid. You put a pipe in the ground and it comes out. You then, in fact, take it to a refinery and take off fractions. Those days are almost over, certainly for this next generation and past it. The key in the beginning will be transportation, and I'll come back to that with fuel cells. If you look at this notion of the evolution of the increasing background amounts of carbon dioxide and other greenhouse gases and their impact, as clear temperatures are rising. The next question to ask is, what is the impact? There are those citizens who would point out, global temperatures go up, that's terrific because Minnesota gets warmer, except it's not actually clear that will be the case. The models that look at this problem come up with different answers, but they're all focusing on certain facts. Fact number one is, regardless of what happens with the increased thermal energy content of the Earth, we in fact can anticipate there will be significant regional climate changes. We can also anticipate there will be increasingly intensive activities such as hurricanes down the road a piece. Is this a problem? It may not be a problem in a specific area, but think about something else. As a world, we're deeply committed to a capital infrastructure that's in place where we are. This includes in this country everyone moving to the two coasts. If we have to make significant changes, and the anticipation is we would, the reinvestment in putting a society back together could be unimaginably costly. And this perhaps is what people are concerned about in the end. I show this slide because, again, it is a straight line projection from where we are now into what I call a danger zone, the carbon wall. Most of these models, these huge massive computers run, would say if and when our carbon dioxide content in the atmosphere reaches this level of 450 to 750 parts per million, then these events that I've described are almost inevitable. That doesn't mean we can't intercept. This doesn't mean we can't re-engineer, but we're talking about significant efforts, not only in science and technology, but in politics and political will, nationally and internationally. So the story began with fuel cells, with an emphasis on hydrogen and fuel cells. Those two erstwhile scientists you saw in this program, I've known since they were graduate students, so I'm very close to this problem, the way they were describing it. There are other aspects of this for us to talk about. If you look at the discussion and where it's led us, you can see that we do have to face two issues, energy supply and the impact of fossil fuel burning on the environment. I would make the point that what really is needed is a coherent national, international policy that looks at all of our energy sources, their impact on health, on the environment. And we need, in fact, to have coherence at three different levels. One I understand very well, research and development. Invest now to make technologies work for the future so that economics can choose amongst them. In between, the transitions between technologies demands political will that goes beyond simple capitalist notions. We have to decide to invest in the future in a very, very straightforward and enlightened way. And if you look, what are we talking about? Hydrogen could be a key, but I'll come to it very quickly and point out it may not be a key at all. Solar. All these energy sources have timelines. Solar energy cells, by extrapolation, in 10 or 20 years will be on most people's roofs. The technology is evolving. It will still represent only part of our energy needs. Nuclear energy. Instead of closing down plants as the Germans are today, we have to face up, as this country is again, after a long, quiet period, to constructing new power plants based on nuclear energy. There are huge downsides. Where does the nuclear waste go? The citizens of Nevada have effectively blocked Yucca Mountain. There are, at the Raleigh nuclear plant, building up, as all over the country, huge amounts of nuclear materials. It's an unsolved problem. At Los Alamos, the other thing that absolutely frightened us was how many North Koreas and Irans can you deal with? As soon as nuclear power becomes a commodity, then nuclear weapons can follow. And so a new international order is needed to control nuclear materials. This is a huge and significant problem that includes solutions that are both science and technological as well as political. Let's focus on hydrogen. As Rob pointed out, somebody managed to get the President of the United States a couple of years ago in his speech to the Congress to point out that this nation should be a hydrogen economy, and I think that's a wonderful achievement. It actually is, because to break into that speech with a technology issue is very difficult to do. It happened. There is a sensitization in Washington. Regardless of your politics, remember, when this administration came to power, the first thing the Vice President did, although he's been criticized for the way he did it, was to bring together smart people to think about an energy plan for the future. An excursion in Iraq has diverted their thinking, but this administration has been very sensitized to these issues. Nonetheless, if you look at hydrogen and look at the bottom, look at the technical barriers to overcome. And I want to, in fact, come back and elucidate those issues because Rob started. And I want to say something about storage, production, and delivery, as well as what one does in terms of technological investment if we actually go down this road. Let me first address the question of hydrogen sources, and Rob started and developed this notion. The amounts of hydrogen that would be required are unimaginably vast. They're huge. We have current ways to make hydrogen, as you can see at the top. They come out of refineries. It, in fact, is a major product, if you look, of methane. You can strip hydrogen off methane now using conventional technologies. You can use, in fact, electrolysis. And the film showed the classic freshman chemistry experiment where hydrogen comes off on one side and oxygen on the other. But looking ahead, for these massive amounts of hydrogen, the only thing that makes sense is to tie it, as Rob pointed out, to technologies that bring energy in to things like water. And if you think about what this means, water is hydrogen and oxygen. And an ideal closed system would involve using an external energy source to split the hydrogen, the water into hydrogen and oxygen, then bring them back together in a fuel cell. No carbon dioxide, cycle the fuel. Hydrogen, oxygen make water and recycle. But you have to have an energy source. There is a nuclear reactor now being designed to be built in the Idaho Nuclear Reservation that is designed to look at cycles for high energy, take the excess heat of the reactor and actually split water apart and make hydrogen. The allusion in that film to solar energy is terrific. I do this for a living, and there's no guarantee it will ever work. But on a timeline, it's one you invest in basic research now and look towards the future. This is a major problem because it would mean huge retooling of how we do business if hydrogen is to be practical. What about fuel cells? You saw that concept car. I've driven both Toyota cars and GM, General Motors. The industry is very excited about this because, in principle, it's a wonderful way to build a car. You have an electrical source that goes to electric motors on all four wheels. The acceleration is terrific. The cars have no transmission tunnel. You sit in the middle, and there's all this excess space. The concept is brilliant. There's a small problem. Looking at current technology, fuel cells are too expensive by a factor of 100. And until somebody, and a lot of this is very basic science, gets much better at making these fuel cells more efficient and more reliable, they're stuck. It looks as if over an extended period of time with significant research, this problem could be overcome, but it's not guaranteed. Yes?
Something I've never understood about this is that if we had abundant hydrogen, we could burn it in engines.
Yes.
As well as burn it in fuel cells. So why do the two things have to be linked so inextricably? That we have to have efficient fuel cells before we can have a hydrogen economy?
There are a fleet of buses running in Phoenix right now, and they put a plug in the wall and make hydrogen. The reason why is that if you look at the cost it makes to make the hydrogen compared to liquid fuels, you need, in fact, to use the hydrogen more efficiently. And fuel cells operate inherently at least twice as efficient as combustion in a combustion engine. And so to make it pay off, it makes a lot of sense. If push came to shove, if you had an unlimited amount of hydrogen, a combustion engine would be just fine. Except for my next point, there's another problem. And I'll end with this, and I don't want to be too down on fuel cells because I like them. I do research in this area. Oh, I'm sorry.
So I actually have a comment. So what you're saying is basically you take the stationary electricity generation and you put it in a fuel cell and you apply it to transportation.
There are two different ways to use hydrogen. One is at high temperature in fuel cells to make electricity. And this is a legitimate way to think about that, and that issue came out in Rob's talk. The other is to take a different approach, low temperatures, lightweight for transportation. And that really is a fundamentally different approach with different materials. And they're both perfectly valid. The real problem with hydrogen, makes me scratch my head about, that Rob alluded to, is storage. So you make this stuff and you pump it in your car. If you look at the cost of trying to store enough hydrogen as a gas, it simply would consume much too much space. The answer has to be in a new kind of chemical material that has the ability to absorb the hydrogen, hold on to it, and then under stress, for example, a little bit of heating, release it. That is an unsolved problem. And unless that problem is solved, hydrogen for transportation may never fly. So let me just finish then. I came back to fuel cells and point out the dilemma we face now, if you start with my initial analysis, that we need to think about global solutions, looking at a number of different alternatives, is that in all the areas that I mentioned, they need additional research and development to generate new technologies. There is a chance that this could fly. It is not guaranteed until the country, in fact, invests more in R&D and then this notion of getting new technologies in the marketplace. We will simply not get to where we have to go. In the long run, in the end, I don't want to be too pessimistic because I do think that there is some progress. Rob alluded to the new national energy policy that got passed by Congress after 15 years, sponsored by Senator Domenici, my favorite senator from New Mexico. That was very hard work, and it's a beginning. What the country needs is that kind of thought process and long-range planning. And I hope and I think, in fact, we're probably entering a period when the people in Congress really begin to appreciate this point. So hopefully we'll move forward as a nation and a world.
All right, well, I think we've had two great talks from two really interesting men. And my thought now, first of all, is once again just to say thanks to both Rob and Tom, and then I'm going to ask you a question. So can we give them another round of applause, please? Thanks, guys. So we're thinking that maybe the next phase of the evening would go best by having our two speakers sort of split up on either side of the room, maybe one of them back over here by this wall and the other one over here by this wall, and allow us a chance to do as those of us do at the end of an interesting lecture at school and wander up to the podium, as it were, and interact a little bit and chat more informally, and allow some of us to interact as well while we're not in our tables, but maybe allow at the same time the cameras to capture some of the interaction that's going on with both Tom and Rob. Maybe Rob would be over here and Tom over here. why don't we all get up and stretch our legs, use the restroom if we need to, and come back in 5 minutes or so, refresh our beverages, and see where that leads us. Thanks.
We are the world's consummate consumers. You know, we generate a quarter of the world's fossil fuel emissions, and this is why I didn't want to. You know, we talked about what the largest sector was, what the rates of increase were greatest in. This is why I wanted to stress it's residential. It's not about big business and all these other places in the world. It's about us.
Yeah, because that's what, you know, if you've got hydrogen, if you stop and think about it, once you make it, it's really pretty cool. So you don't have the problem.
Yeah, but I mean, I think about all the smog here. You know, just you know, what happens, I mean, when the fuel cell doesn't wear out after like 3 or 5 years because of all the other stuff in the air.
Hydrocarbons, yes. And it's a major unsolved problem. Okay. Hydrogen in principle, no, although GM has run hydrogen fuel cells for, basically the equivalent of multiple years. They're pretty happy with performance. Okay. But you still have to be careful. I mean, if you put too much junk somehow in the gas stream, like in the air, it will poison the catalyst to death. So you've got to, these high-tech solutions oftentimes have that disadvantage. Okay.
Do I decide to sell a fully paid off vehicle that's not yet depreciated? I mean, we're talking thousands of dollars to buy a car that's going to save me, frankly, not enough. I mean, 20 years ago, I drove a Honda product that got 50 miles to the gallon, or 55 miles to the gallon highway. The Prius isn't good enough.
I mean, no, it's a great question. But this ties directly into the discussion we have. No, it's true though. I mean, it ties directly into the discussion too about coal plants and nuclear plants. What we put on the ground now lasts for a long time, and that's true for our automobiles as well.
But as an individual, I'm not penalized enough to make me change.
I mean, one way to do that would be through an extremely unpopular choice now would be a gas tax, a carbon-based tax. And the way to make that politically feasible and palatable to me as a taxpayer would be to make it revenue neutral. And Paul Anderson from the CEO of Duke Energy recently came out publicly, I think the first energy CEO, to say we ought to have a carbon tax. You know, why would an energy company suggest that? The reason is because they don't want a mosaic of regulations in California doing one thing, the Northeast doing another thing, North Carolina do another thing. They want the feds to level the playing field and then live with that. And they also want it spread across all sectors of the economy, not just utilities. They want cars. They want, every sector. So you're absolutely right. I wouldn't recommend, unless you choose to do it for personal reasons, I wouldn't recommend selling a car that you own and is paid off for a hybrid until you need a new car. Then I would say evaluate a hybrid. But it's not realistic to say everybody in this room, go trade your car and buy a hybrid. I mean, that's not feasible advice to people, in my opinion.
If you look at geological maps, and I've seen these, almost every country in the world has got geological strata that are accessible. And so the estimates that I've seen is that you can use those strata, collect the CO2, pump it in the ground.
How do you collect
20% on your electricity?
How do you collect the CO2? Do you just do it at the tailpipe?
It's done now. The Norwegians have been collecting CO2 and putting it in storage under the North Sea for 10 years.
So you basically set up power plants and have it right there.
Yeah, in fact, look, there's a pipeline that goes from western Canada down to Texas, carrying carbon dioxide as gas. They pump it out of the ground because it's in huge amounts, some of these reserves. And they send it down to West Texas oil fields and pump it in the ground. And that the CO2 goes down, interacts with the rock surface and releases oil. So it brings these oil fields back to the ground.
Well, sea creatures turn carbon into chalk.
Yes.
Could we develop microorganisms that would do the same thing?
Yeah, but that scares the hell out of people.
Take over the world.
No. The thing you worry about is the amounts of CO2 involved are unimaginable. Unimaginable. And so I've got this hour-long talk, public talk I did, and to go through some of this. If you look at the total amount of carbon dioxide we're releasing, and if you look at where it could go in the year 2100, say nothing is done, and all the CO2 just builds up, there would be more CO2 in the atmosphere at that point. This would be an increase of like 50, whatever we are now. It would be more than all the plants and all the soils. You could, in fact, put it all in the ocean, but then pH of the ocean, CO2 is acidic when it's water.
CO2, yeah, but is chalk acidic?
No, but you got to pump it. You got to pump it in the ocean. And the sea creatures will become more efficient using the CO2.
Oh, yeah. Well, I was thinking, can we do it without putting it in the? Can we do something that, CO2 in one end, chalk out the other, and maybe some genetically engineered microwaves?
Trees are more efficient.
Trees are more efficient.
Yeah, and look, that'll be part of the deal. That really will increase biomass and use geological sequestration. It might be 3 different ways, 4 different ways. The only thing I would say is the ocean is controversial because if you start pumping it way down in the ocean,
we can't raise the pH of the ocean.
Good point.
But all this rising CO2, it's coming from what? That's the fossil fuels that we burn and coal.
Guys, in the spirit of the evening. Is that one mine?
I think so. And it wasn't mine.
Have some nuclear power.
Well, that's what we've been doing for 20, 30 years.
Well,
But it's a cost view that does not take into account, the downstream costs of the pollution or lots of other things too. But it
kind of what clean smokestacks seem to attempt to do.
Yeah, that's right. Yeah, it's to take a broader view of what it's costing us, in healthcare costs to breathe air.
Who's going to take that broader view? We can't even agree that there's, environment, that there's global warming. I mean, we've got an administration that won't even admit to that. I mean, it's hard to imagine somebody taking a long, broad view in this climate where, even something that's like scientifically provable is up for grabs.
Yeah, you're right.
You guys are endeavors.
I mean, I'm somebody who,
that's one of the better,
was around when Jimmy Carter said that. I thought for sure, putting it on the table, it would be dealt with 20 years down the line.
No, isn't it amazing?
I know. I mean, when you said that about the Model T and today, that is. I've never heard that before, but that's where we are. It's like we got the message, but we just decided to, not do anything about it, and here we are.
Yeah, I don't remember the exact numbers, but it's something like if we had continued on the relatively mild trajectory that Carter outlined, we would need no Middle Eastern oil right now.
Back in the mid-80s, the other part was